Okay, they have it there. Perfect. So
have you run into emergent gameplay, an emergent system?
do you know Clay Reynolds? No, but it's the super guy who this Reynolds model for multi-agent systems that it has been used in computer graphics. So he's one of the fathers of multi-agent systems and modern logging. So yes, it is used in the game.
The kind of game I'm talking about is
sorry,
it's not this. Yeah, it's different kind of game. Good.
Formal, and then when you say the game,
you see this show up in the world of game design, which is called it has what's known as emergent gameplay. That is that you can spend years designing a game, and the players come in and then become something else.
Yeah, absolutely. Yes. We'll come back to that, but it is something else. That is social behavior too. But we can come back to that. And also, I don't know if you have heard the thing of a small world property. So that we say 6 degrees of separation, that anybody in the planet, 2 people completely randomly chosen, there are at most 5 nodes, 5 people between all of us. That is the small world property, and there is a theory, complex network, that formalizes this. So it doesn't matter how big we are, because there is a very small path connecting nodes in a very big system. For me, this is mind-blowing from the viewpoint of mathematics. When I started studying this many years ago, I said, this is fantastic. Okay, but it's not only about the topology. So it is about dynamics too. So we have the emergence of, and I repeat, dynamics. Because I am a computer scientist, but I am also a control engineer. And I know that in computer science, time and dynamics are not very useful. Formalism. So, but I repeat and I repeat, this is the emergence of dynamical behaviors and patterns. And we model this with what we call networks of dynamical systems. And there is group cooperation and competition, what we call collective behavior and self-organization. So I could put a lot of pictures about examples of group formation and collective behavior. We gave the example of the flock of birds. We have the school of fish. But I always thought when you love something, when you love your research, you see it everywhere. So these pictures are from this book from 1941. I was coming from Oxford, and I was working with my colleague Maria in modeling bee behavior. It is a kind of the essential paradigm for swarming dynamics and swarming intelligence. So I was in Manchester, and we were in a pub, having a drink, and then I looked up, and in the shelf, it was this book, The Social Life of Animals, 1941. This is not new. So these pictures are from this book, because I could put many photographs that I have made myself for the, but I love this photograph because my point is that this is not new. So we have ladybirds that they congregate, we have niches. When you are in the forest and you see in the summer or the light of what is the name? Niches. Yeah, but now I can't remember what I was thinking. Okay, social lives of animals. So what do we have here? We have here self-organization. It's some kind. Is it that from the viewpoint of philosophy, there is a kind of okay. Okay, it's okay. I'm going to say it. Self-organization philosophically is the local versus the universal dynamic. So we have a collective behavior that emerges in the absence of any centrality. This is amazing. So there are local rules for the individuals that lead to global patterns. What is the point? What can I say? Because then I get excited. Yes. Yeah, I'm going to put here, because then I get excited and I can be here everywhere. Okay, so yes, so this is what we have. And now why this is not working? So pattern finding, the past. Alan Turing, do you know that the father of the most cited paper of the father of artificial intelligence is not about computing? Did you know that? The most cited paper of Alan Turing, the father of artificial intelligence, is the chemical basis of morphogenesis. Have you ever listened to morphogenesis? Okay, I have worked with the last student of Alan Turing in morphogenesis. Morphogenesis is that in 1952, when he was in Manchester, so he produced, he was a genius, he was a visionary. So he felt that he has done everything in computer science. So he was very curious, observing everything around him. So the model of morphogenesis is a mathematical formalization. The first time that it was formalized, growth in nature and how forms appear in nature, patterns. So it is, but patterns in cells too. His first idea was, okay, what happens when we have an embryo and all the cells are the same? What happens and suddenly you have cells of your heart, cells of your lung? Have you ever thought about it? So that can be formalized. There is a break of stability, and then we have different organs. The same happens in nature. So we have different shapes, so the zebra patterns, so patterns in animals' coats. This was the motivation of Turing. And I studied all of that, and then I saw it from the viewpoint of dynamical systems. So what you have, okay, the theory of morphogenesis, what Alan Turing did, was the reaction and diffusion processes in morphogenesis. This model is essential now in mathematical biology, and now nobody put attention on it, and then in the 90s, now it's used practically for everything, for everything, even in architecture, everything. I have even created music with this. Okay, so you have reaction and diffusion processes. Reaction is the local. I'm not going to go in there. And then you have some kind of local behavior, chemical behavior, and then you have the diffusion behavior, that is like the global behavior. And then suddenly there is an instability, you break homogeneity, and then you have the growth or differentiation of cells, for example. That is the self-organization. This is Bernard Richards, that took the baton of Alan Turing. And then Alan Turing said to him, okay, what you are going to do, I have done a model in 2 dimensions. Now you are going to take my model and you are going to find the solutions in 3D. And then Bernard, what is this? So what you are going to do is going to the library. You are going to take a book of radiolaria. Radiolarias are marine organisms. They are beautiful organisms in the sea, and they have these incredible shapes because of the salt of the sea, and then it produces this incredible pattern formation. So beautiful. So Alan Turing was saying to him, what you are going to do with your models is explaining the growth of the creature in 3D. And then Bernard did it. So this is the Manchester, this is the Ferranti Mark I, 1951, the first commercial computer in the world. So, and Bernard put the equations, typed it in a tape, and then the machine calculated, and then this was the output. He reproduced, he found the solutions to reproduce the forms of radiolaria. And this is 1951. I mean, this is amazing for 1951. Sorry, this is the solutions of the equations 1954. So this was the Alan Turing was dead, and Bernard presented his work 2 weeks after Alan Turing died. Okay, so it's my story of Turing, Richards, and I say morphogenesis and me, because I have been obsessed with Alan Turing. I have met all the pioneers of computer science, all the people that built the first computers, and I think so. I wanted to put a video because I have a video. What is my video? I have a video. I thought that it was going to work. And so morphogenesis. Okay, I thought I had put the
I put a video, I put the link in the presentation. Okay, so now I cannot find the video, but it is okay. I was putting the video of how to, because it is in Google, I have opened in another. Okay, it doesn't matter. I was putting an example, a video of how, now I cannot find a video. I don't know why, but I was putting a video that I did with one of my students that we reproduced with form patterns with the equations of Alan Turing. And thanks to this, I have been lucky enough to make a very modest contributions to all this work of Turing. I met Alvy Reyes-Smith, the co-founder of Pixar, and I made a little contribution to his last book, and also to this book of Alan Turing's Manchester. So, yeah. So morphogenesis is the basis for what later was called self-organization. So reflection number 2, where are we now? So for me, the basic question that it hasn't been solved yet, and now is a problem, is the golden, what I say is the golden question in evolving complex systems and networks. It is connecting the network topology and the dynamics. So in the world of complex network, the topological properties we analyze with different models. We have random graph networks, we have small world networks, and scale-free networks, basically. We have more models. But look, depending on the topology, we can reproduce with different paradigms, computational paradigms, different shapes. But also we have network dynamics, because self-organization, and emergent properties are dynamics. So we need a collective behavior that we can describe with dynamical systems, and we can reproduce all this type of behavior. The problem is connecting this. How the topology influences the dynamics and how the dynamics influences the topology, and how we can model that. This is something that now, today, there is no answer for that. And I am trying to find an answer for that. And now I'm going to present some recent work that I have done, but just to show the importance of data in all of this, to understand the topology and to understand the dynamics. So it is very important, the data measurement and the processing for complex systems. So this is a one work that we did with Oliver, my PhD student in Manchester, and what we did is new models of evolving complex networks. And our test bed was we took data for more than 1 million open source software projects written in different languages. And then what we did is to visualize and analyze the dynamical properties of these communities, and we saw how they evolved in time. Communities of Python, communities of Elm, communities of different languages, communities of Elm, principally. So this was, theoretically, it was an intense work, but also it was nice that we see the evolution of these software dependency networks. And we saw the beauty of open source projects, because we saw how different models were used by different communities. But it was more than 1 million projects that we analyzed. But look, the beauty of this complex network. You visualize it and you understand it. This is my work with Harry, my PhD student in Manchester, that is finishing in the next weeks. So we have done is that we have formalized the evolution of the communities in the metropolitan area of Manchester. So we have analyzed, this is transportation networks. And this is very beautiful because we are working with the Manchester Council and the 9 authorities of the Manchester region. And then we are giving them tools for making political decisions. So we are seeing the evolution of Manchester in the past 40 years. Theory of complex networks. And something a bit different with Rogelio. Rogelio, I send you a hack because I know that he's listening. So this is a recent work with Rogelio, is that we are creating new neural networks architectures for medical imaging analysis. But the most important thing for us is not the applications of analysis, in this case, of endoscopy images, is a very nice work that we have detected different, better than other techniques, problems in endoscopy images and types of tumors. This is very nice, but for us, what motivates us is that we are creating new neural architectures based on the brain. Okay, but I say always that the network models, they are too much focused on topology. And we need to go beyond network science, because the theory of complex networks is not enough, because it is a more statistical approach than behavioral. And again, complex systems has dynamics. It's not, and you cannot put dynamics in a statistical model. It has limitations in the analysis of dynamical properties. It has limitations in the analysis of evolution and adaptation, because evolution and adaptation is a dynamical behavior. Like what is happening in my brain now that my neurons are dying. But also it's very important. These models cannot consider switching and discontinuous dynamical processes. I have forgotten my bouncing ball, because I always my bouncing ball, because it is the example of the most simple highly dynamical system, switch dynamical system. Yeah, I forgot it at home. Yeah, I always have in my office always are full of toys and things, but I have forgotten. I don't have them in my office. So okay. So it also, these models, they fail to reproduce goals, varying goals. I am a person that comes from control. So for me, control goals are very important in dynamical systems. So you have to have some goal of behavior. And there are feedback in these systems. Okay. So these are the limitations of complex networks and all this theory. So reflection number 3, where are we going? Okay. What we should be going, from my viewpoint, is that we need a general framework to solve this problem. How to model the relationships, what I was saying before in the present, between subsystems, the local behaviors, and the global topology, evolving topology. And how the dynamics of the local, the local dynamics of the systems influences the evolution of the topology, and how the evolving topology influences the local dynamics. And don't forget that we have networks of systems. How all the interconnections affect the subsystems, and how the subsystems modify the interconnections. There is not a general framework that can explain this yet. And then you will ask why? Because it's a very complex thing, more than complicated. Because we have continuous and discontinuous dynamics, like the bouncing ball, at different levels. It's a multi-level modeling problem. Because we have a network topology that evolves. Because we have control interdependent mechanisms. And because we have evolution and adaptation everywhere. In the dynamics, and the topology, in the feedbacks. And all of this creates an emergence of collective behavior that changes with time. So how I have a right to do this, how I have a right in my life to come to this question. Okay, so my life has been from building robots to producing models of the brain. And in the middle, but I have seen brains. I have seen real brains. I mean, like in control, they will say, oh, you need to know your plan. Yes, I was in control. I have known my plan. I was in the Institute of Cajal with rats, with brains, and then I was trying to convince the people that I don't know if you know, but neurobiology, all the experiments that are done, that open the brain of the rat, they put the sensors, and the rat never recovers. So every time that you see a paper with some measurements of the brain, think that more than 10 rats have died for that. So brutal, completely brutal. Neurobiology is the most brutal area in biology. I mean, they don't care to kill all the rats. One weekend, I was thinking of liberating all the rats. But I said, Eva, I want to provoke here a bit of a mess, so I decided not to liberate all the rats. Anyway, so I have seen real brain. So I know what I am talking about. So in the middle between building robots, I was one of the first persons in Spain who built walking leg robots. So between robots and the brain, I have done many different systems. I have worked in mechanical systems. I have worked in mechanical vibrations in the oil industry. I have controlled different types of robots, power electronics. I have studied ecological systems, smart grids, social networks, cancer dynamics, and I have even created music with swarming algorithms. So my journey has been always between Alan Turing and Ramon y Cajal and back. Like a control engineer, I see feedback everywhere. And I am trying hard to follow the steps of Ramon y Cajal. This is a photograph of Ramon y Cajal was known because he liked to do selfies of himself. Ramon y Cajal is the father of neuroscience. And then this is in Ramon y Cajal's institute, and I'm trying to pose exactly in front of his desk. This is not his desk, but his desk was there. But I couldn't sit down there. But okay. Cajal was another genius, was an artist too. Anyway, so in these times of artificial intelligence without artificial intelligence without intelligence, where a linear regression is called artificial intelligence, and statistics is called machine learning, and deep learning, it seems that is the only computational paradigm that it has ever been created. I think so they will have to go beyond it and challenge the status quo and propose new ideas, models. And then I propose for threads of thought. And all of these form my laboratory of AIDAs that I hope so, artificial intelligence and data science, that I hope so that I can build here or move here. And ADA, I have in these AIDAs, I put in capital letters ADA, which is a homage to Ada Lovelace. So the first thread of thought is nature-inspired intelligent machinery. And this is, I don't know if you can detect this for people who have read the work of Alan Turing. Intelligent machinery, I think so, is the beginning of artificial intelligence, 1948. If you haven't read that paper, I would advise you to read that. Nature-inspired intelligent machinery is the manner that I say that is the formalization of intelligence in nature and in machines, but with a special focus on cognition and collective learning. And it is, and I have created a framework that I call hybrid neurosystems, that it is based on the theory of hybrid automata. I come from a very core computer science and dynamical systems background. So it's the merge of these two areas. And the second thread of thought is using these ideas for modeling complex systems and analyzing them. Complex systems that they have self-organization, evolution, and adaptation, those emergent properties that we were saying yesterday. And talking about properties, when you have these kind of systems, we cannot analyze them so simple. So we need to automate this. So we have the area of automated verification and reasoning, hybrid dynamical systems that I am one of the world leaders in this area. And then the last area is what social computing is, a new area that is coming, that it is more than computational social sciences. It's not the use of computational paradigms to study social interactions, no. It is the mixture of machines and humans and see in large scale and the type of phenomena that is produced. In my case, I am analyzing the evolution of communities and social interaction. So those new models that I was saying that I call hybrid neurosystems are based on the idea of Turing's morphogenesis. The basis, I don't know if you know what hybrid automata is. Probably not. Hybrid automaton is an automaton that in the locations you have a dynamical system. So then you mix the world of automata, all those discrete abstractions, and also the world of dynamical system. And then what I do is breaking the connections between those locations. So the automata, that is a switching system, like the bouncing ball, like a thermostat that it changes in different states. What I do is breaking the topology is going to evolve with time, and you are going to have edges or links that they are going to change with time. This is quite a complex manner to abstract this is quite, because you enter also in the world of logic. Okay, so yes, I could give a talk of this whenever you like, of every slide. An example of this type of systems, hybrid neurosystems, will use these concepts to model the basal ganglia and thalamus and cortex in the brain. And thanks to that, we have devised models for the working memory and Parkinson's disease. So we have had quite complete models for this. And what we use is what I call the octopus hybrid automaton. So what you need to understand is that it's a multi-level problem. It doesn't matter the details of the equation. So you have a local dynamical system, then you have a population of this dynamical system, and then you have a population of populations. So it's a multi-level. Divide and conquer. With these complex systems, you need to divide and conquer to make the models. And then that line 3 that I was talking is about analyzing safety and security critical systems. So they are everywhere. They are dynamical systems, complex systems that we need to analyze and automate the analysis of it. All these systems have software too that needs to be verified too. Okay, so this is me in my desk with all the equations of these systems, and I'm trying to analyze the dynamics by hand. There is a moment that I can't, because I have how on earth I'm going to simulate all the scenarios, all the parameters, all the inputs. So I need to automate this. And how I automate this with the world of automated verification or formal verification. So you have a dynamical system. You have some properties that you want to verify, but you need to automate this. You need discrete abstractions of the dynamical system. So what you are doing is, this is some engineers here. So we have what is called the V cycle for testing, validation, and prototyping. Somebody here that has built an engineering system will follow this when you, but what I'm talking here is that the first part you automate it. So you automate the part of modeling and control. The first part, when you are controlling a system or you are going to build a system, so the modeling part and the pre-analysis part, we automate it. And again, Alan Turing was the first to propose automatically to check. So he's some kind of the father also of formal methods of computer-based theory improving, which is one class of automated verification. So this paper also was done in Manchester, and if you haven't read papers of Alan Turing, I advise you to read it, because with some kind of this clear thinking, the abstracts are so good. So anyway, so he started to do this. So 3 challenges in automated verification. So the format, you need to have a formal model of the physical system that has different types of dynamics, continuous, and changing over time. You have complex and unpredictable interactions with the environment, and you have different operation modes. The second part of this process is the formal specification of these properties. Now we enter in the world of computer science, the discrete abstraction. So you need to specify logically those properties that the system has. But you have different types of properties. So you have safety properties, lightness properties, reachability properties. I can give a talk of this. This little book, I can give a talk about it. So, I have, okay. And you need to have temporal logics. So you cannot use the classical logics because you have time here. The last part of this process is check automatically that this model meets the requirements that you have defined here. This model meets these requirements and you automate it and you do it with different verification strategies. Model checking, deductive verification of theorem proving, or reachability analysis. What is today's challenge? Verifying this in highly dynamical systems, like the bouncing ball, but a little more complicated than that. So we have physical systems with different operation modes. And the formal verification process is that you have informal requirements, like we do in engineering. You have a formal specification, you push a button and you say, come on, tell me if I have if this is correct or not. And then you say it is correct or it's not correct. It's not as simple as this. It's a very complex process. And then the last part that I was talking about that I am working on is on social computing, but I would like to say, but there are many different types of brains in collective intelligence. So we have the human brains, we have the collective intelligence, also collective artificial intelligence, and also we have social minds. We have a kind of a global collective learning that I see is the complex social networks that we now have. That is the mixture of machines and humans, but in large scale. And as a conclusion that I would like to have today, the ideas to take home, is thinking about adaptation and evolution in dynamical systems. And I think that there is something wrong that is happening now in the area of artificial intelligence. Again, deep learning is probably cannot be even considered that has any intelligence. And that type of model that has no elegance at all, how can there you know, I mean, for me, all these models are elegant. They are difficult, I know, but they have a logic, you know what you are doing. But those types of models like deep learning and nobody knows what is going on, I think so that that is not science. It is something else. Okay, so we need to know how to model adaptive dynamical process in the brain, and that is very hard because the dynamics and the topology changed over time, and we have self-organization, and we need new models for new kinds of systems today. There are many names. You can help me to say me some new names. Evolving hybrid learning systems, cyber physical systems of systems, collaborative systems, cyber social learning systems, cyber physical human systems. At the end of the day, the conclusion is that we need to consider dynamics. And the most important thing is that it's a very multidisciplinary problem. So we need to mix control engineering, dynamical systems, computer science, logic, mathematics, artificial intelligence, data science, and everything that we have at our hands. So if you want to see more work that I have done, I have tried to summarize in the future, in this reflection of the future, but you can go to my webpage, and this is what I wanted to present today.
So we have about 10 minutes for questions. I will say that we only have the mic on the laptop. So you may want to come a little closer to ask the question, or I might type
Yeah.
the question into the code online.
And there are questions also.
We can go. Well, does anyone have an immediate question? Whether that's on Zoom, if you raise your hand, I can pull it out.
I just have,
Okay, Bruce, yeah.
so, right at the beginning of your talk, you did the Menzi.com. Can you tell us a little bit about the background on the?
Sorry, the Menzi what?
Menzi, sorry, where we put in the terms.
Oh, I forgot. How is it going? Oh, yeah. How is it going? So that is the example of a collective thing. Oh, so how are we doing here? Have we changed the concept? Self-correcting, yes, self-modifying, more than systemic principles implicate healthcare workflow confusion. A complex system is not confusing. Tangled, digital, ChatGPT, multi-layer, yes, feedback, organized. ChatGPT is not so complex. I mean, it's not. Okay, there are some studies that suddenly what it is happening is that there are unexpected behaviors of the tool. But remember that the tool doesn't think, it's just the accepted plagiarism, is taking text that everybody has published in the internet and through statistical techniques, it's choosing with probabilities what is the best next word that it comes. For me, it is not a complex systems, it is another thing, but it's not a complex system. Some people say that they are having unexpected behaviors. Yes, because it is an approximation. But for me, probably it doesn't fit in this. It doesn't interact with the environment, it doesn't have evolution, it doesn't have adaptation. Yeah, but that can be challenged too. And I would like to be challenged. But yes, so sorry, ChatGPT is something that it drives me crazy. And in the department we should talk about it. The use of ChatGPT in the class, by the way. Anyway, I am diverging. So yeah, so this is so good. It doesn't change much yet from the beginning. But now this is an example of a collective behavior. We all together did this. Some more questions? Yes, Dave.
So, one of the things I actually do with the bouncing ball, I actually do this with my students. Take 100 marbles, put it into a box, shake it. So in the world of graphics, games, particle systems, its collision detection and response is extraordinarily difficult.
No, I can tell you, I have
Yeah.
looked at systems with impact. Oh, you can, I could give a talk about that.
Yeah, because I'm saying there in the world of SIGGRAPH,
I
the
know,
whole other talk about smooth particle hydrodynamics.
I have worked with people, yes.
And so I guess the short version of the question is, where does this work intersect with your typical SIGGRAPH graphics approximations?
I don't know, I don't work in computer graphics,
Yeah.
but I have, yes, particle swarms, swarming dynamics. I told you, Reynolds.
Oh, right, oh, Craig Reynolds, yes.
He's one of the fathers
yes.
of those models.
Oh, sorry, I did.
Oh, sorry, my friend.
Yeah, I'm sorry, that's me. Yeah, that's Reynolds, yeah, we do this in IGM quite a bit.
Yes, blocking
Yeah.
dynamics. Blocking dynamics.
Because if you think of fluid simulation, we're really going from the discrete
Oh, that
to
is
the,
another thing. That is another thing.
yeah,
You have partial differential equations. But what I wanted to show here, you know, I have modeled with hybrid automata systems with impact and friction. That is the worst discontinuity you can have, and you cannot imagine. I could show you. I mean, it's more complex than anything that you can imagine. Because dynamically, well, you have one pass involved, two ones involved, 3, 4, 5. You cannot define, we have 500 or 200, I can show you, this is my work rate.
Yeah, and
And
what,
we even automate the generation of those models. Because there is a moment that you can't. I was talking with my friend Marcela, and we were planning to use my work for her work in computer something.
Yeah.
About this impact modeling, but we didn't have it. But you have an automatic tool of 3 states, and suddenly you have 1,000 states with only 4 models. It is amazing, but why is that? Because of the dynamic. Because mathematically there are some bifurcations that are caused that produce unpredictable behavior, and it's crazy. I mean,
yeah, in other words, you're stumbling on one of the classic unsolved problems of computer graphics, which is when does computer graphics become physical reality? And the,
so probably you need
Yeah.
to use this model.
Yeah, but-
Yeah.
okay, so I figured what that. Yeah,
And impact systems with friction. I can tell you that, wow,
yeah, a lot of folks still realize just the intensity that our students at IGM are going through to try to
no,
solve commonly problems of course. It's extraordinarily complicated. Yeah. Yeah. It's more I'll follow up with you.
complicated and difficult. So I don't know who can say that.
Yeah, at this. As soon as making it easy.
Yeah.
Do you have some questions online or?
Oh.
or-
No,
okay.
there's none at the moment.
Okay, so Ella, can you please talk at the end, you kind of wrapped up with that you're interested in the neuroscience and working with brains.
Yes.
And so can you you speak a little bit more to like where that's going and
Oh,
gave us some background about the.
yes, I could give it. I can give it whole book. The whole hour. So the model that we have done, yes, this model is making a complex network of different regions of the brain. And precisely is the communication, the cortex, the basal ganglia, the thalamus, and part. Okay. But mathematically it's a complex network, and also we have the dynamical complex. But my future, what I want to do is modeling neuroplasticity. But using the energy in the brain. And we have, with Rogelio, we are using those ideas to generate new architectures and neural networks. But my dream is modeling the neuroplasticity of the brain and the real one. And maybe my future. But I have models, I can pass you. We have a lot of models of the brain. That model of the Parkinson's disease is quite a good one, because we have reproduced different Parkinsonian states. Yes, and also processes of the working memories. So yes, basically we use dynamical complex network. So call it the area of neuromorphic computing and computational neuroscience. But the real brain, real. I can be the doctor, no? I can be the doctor.
You can be the last question.
Yeah.
Just because I'm aware of the time.
Yeah, I think in the second half of your talk, you identify, I believe, 4 very interesting line of research, right? So it's L1 to L4, right? I think it's line of research or layers of research, right? I wonder, I think you have one slide summarize all 4 directions. So I wonder whether, you don't mind, are there any connections between them, or they're
Yes.
all independent?
No, they are not independent because one fits the other.
I see.
Yeah, because because these are models, these are new models of intelligence.
Yeah.
That for that you need to modify
Mhm.
the current hybrid automata, and then you use that to model complex systems, the brain,
Mhm.
and then those models you use them for verification as the basis of verification. So it is like a cascading.
kind of
Okay.
sequential.
One thing is, so
Yeah, yeah.
in control, you always have, you model, okay.
Mhm.
You study your system, you generate, you see the system that you have, and you say, okay, I need a new framework. Because the ones that doesn't exist, that exist now, cannot integrate all these things, okay. You have your model, you analyze it first with tools for dynamical systems, but then you say, okay, so, but I need to automate all of this, and then you go to the automated reasoning. And then the last part, I don't know if it is related or not, the social computing could be separated from line 1, 2, and 3.
Mm.
But it could, but my idea is using all the 3 for the social computing. So in the part of social computing, the results that I have now, it is in the evolution of communities. This work and this work. So everything is related because all your life you use
Yes.
what you have used before. And then doing it more complex, more complex, more complex. Adding layers of complexity.
Okay, I think with that, really thank you.
Oh, yes. Thank you for coming. So we didn't have questions in the Zoom.
So